Imagine stepping onto an airline and noticing that there's no captain and no co-pilot. It sounds like fiction, but yet pilotless airlines are rapidly becoming a reality. Modern jets already handle much of the flying autonomously. In fact, today's airlines can already take off, land, and cruise, all using their onboard computers. In this video, we'll explain the technology that allows the airplane to fly safely without a pilot on board. From advanced autopilot controls to navigation systems to AI making decisions. We're even going to look at real-world examples, from autonomous drones and cargo planes to experimental projects. Before we dive in, we have to consider a milestone that happened in 2021. A Cessna Grand Caravan turboprop completed the first fully autonomous flight, gate to gate, with no one on board. And in 2020, an Airbus successfully taxied, took off, and landed, all using its own cameras and AI. These achievements highlight that the age of pilotless flights could not be a distant dream. The fundamental technologies are already here, so now let's explore the key technologies enabling pilotless aircraft to fly safely and effectively. At the heart of any pilotless plane is an autonomous flight control system, essentially a supercharged autopilot. Autopilots have been the standard in aviation for decades, enabling the aircraft to keep its course, hold altitude, and even perform complex approaches. In modern airlines, autopilot and autothrottle systems can handle most of the journey from shortly after takeoff to landing. For example, many commercial jets auto-land in low visibility conditions using instrument landing systems. However, pilotless flights requires going a step further, including parts traditionally done by humans, like taxiing on the ground and the initial takeoff. So how does it work? Essentially, engineers equip the aircraft with electronic actuators and control computers that move all the same controls a pilot would. The yoke or stick, rubber pedals, throttles, brakes, but all under computer command. A great example is the technology added in Xwing's autonomous Cessna Caravan. It included an autonomous flight control system that actuated every control surface and system. In other words, the computer can steer the plane on the runway, lift off, adjust the throttle, climb, cruise, descend, and land, all without a human hand on the controls. The system follows a pre-programmed flight plan or instructions from its AI, much like a highly advanced autopilot coupled with flight management systems. Crucially, these flight control systems are built with redundancies and fail-safes. Commercial aircraft autonomy borrows safety design principles from traditional avionics. Multiple redundant computers and sensors cross-check each other, so if one fails, another one can take over. The goal is to meet or exceed the safety of human pilots. For instance, Reliable Robotics has developed a continuous autopilot that stays engaged through taxi, takeoff, cruise, and landing. Their system is being designed to reduce common causes of accidents. They achieve it by managing the aircraft more precisely than a human might in adverse conditions. It can even handle engine power and minor adjustments continuously to optimize the flight path and stability. Today's autonomous flight control systems have demonstrated impressive capabilities. We've seen autonomous takeoffs and landing in testbeds like the Airbus ATTOL project, where the aircraft computers controlled the entire flight from pushback to touchdown. In the military realm, large drones such as the Global Hawk have long flown fully automated missions. They take off, navigate halfway around the world, and then land on a preset program. The next piece of the puzzle are giving the planes the eyes and ears and brain to understand its environment and make safe decisions, which brings us to the sensors and AI. Navigation is a fundamental part of the autonomous flight. A pilotless airplane must know exactly where it is and where it's going at all times without a human input. Modern aircraft rely on a suite of navigation tools that autonomous system can leverage. GPS receivers for precise global position, initial navigation systems that track the moment and altitude, and often ground-based aids like VOR and ILS for approach guidance. Using these, the flight computer can follow a flight plan route just as a human pilot would, but with even greater consistency. High-precision GPS and advanced onboard sensors allow the autopilot systems to hold an accurate course of altitude and even perform landing approaches with minimal error. Autonomous airlines also use flight management systems, which are essentially the navigation brains that store the flight plan, waypoints, altitude, and speed. The FMS directs the autopilot and throttles to follow the program route from departure to destination. In a pilotless scenario, the route could be uploaded by the ground operators or programmed in advance. During flight, if the plane needs to reroute, a human supervisor on the ground might update the flight plan, or in the future, an aircraft's AI might compute a new course by itself. In Airbus recent demonstrations, for example, an autonomous system was capable of generating a new flight trajectory on the fly during an emergency drill. It was able to take into account the airspace, terrain, and weather constraints. This shows how autonomy goes beyond just following a route. It can also intelligently plan one. Precision is key for taking off and landing, the phase where navigation is most critical. Pilot technology uses a combination of GPS and onboard sensors to ensure the aircraft lines up with the runway accurately. For instance, Airbus's project integrated computer vision with GPS to achieve such precision that the airliner could reliably find and land on the runway without human help. We're also seeing the development of ground-based augmentation systems and satellite enhancements that provide centimeter-level GPS accuracy, further ensuring the autonomous plane knows exact position and relative to the airport. In summary, advanced navigation systems enable a pilotless aircraft to help find its way just as an advanced navigator would. With consistently updating the position data, the electronic flight charts, and the predetermined flight plan, the aircraft knows where to fly and how to get there efficiently. Knowing where to go is only half the battle. The plane also needs to perceive what's around it to fly safely. That's where the sensors come into play. Human pilots trust their eyes, ears, and radar displays to understand their environment, from other aircraft in the sky to obstacles on the ground and weather ahead. In a pilotless aircraft, an array of sensors take on this role. They help feed data into onboard computers so that the plane can see and sense its surroundings. This sensor suite includes radar. Many autonomous aircraft are equipped with radar for detecting other aircraft or obstacles from a distance. Weather radars also help identify storms or turbulence so autopilot can divert if necessary. ADS-B receivers. ADS-B is a technology where aircraft broadcast their position and altitude. An autonomous plane can listen for nearby ADS-B signals to track other aircraft in their area. Cameras. High-resolution optic cameras can give the system visual input, much like a pilot's eyes. Paired with computer vision algorithms, cameras can recognize runways, detect obstacles, or even read airport signs and markings. LiDAR, laser-based ranging, builds a 3D map of its environment, useful for on the ground to spot obstacles on the taxiway or birds and drones in low-altitude flight. Ultrasonic or infrared sensors. These are usually on smaller drones, but are used for precise altitudes during landing or detecting proximity to the ground. All these sensors perform a perception stack. Xwing's autonomous caravan, for example, carries a detect and avoid system that fuses data from radars, ADS-Bs, cameras, and LiDARs to detect any potential hazards in the air or on the ground. The DAA system works continuously and is coupled with a flight control computer to automatically avoid threats if they arise. This means that if another airplane or a flock of birds encroaches on its path, the autonomous plane can sense it and alter its course or altitude to maintain a safe distance, all without a pilot's intervention. On the ground, sensors help to autonomously taxi and take off. Cameras and LiDAR can identify taxi lines, other vehicles, and debris on the runway, allowing the system to either stop or navigate around those obstacles. It's a dramatic illustration of sensor capability and Airbus's achievement. Using solely onboard cameras and AI-based image recognition, an A350 test aircraft could perceive the runway environment and execute a safe autonomous landing. In one scenario, Airbus could consider unusual corner cases, like an elephant on the runway, to ensure the vision algorithms are robust against an unexpected obstacle. To process all these sensor data, powerful onboard computers run sensor fusion algorithms in a machine learning model. They combine inputs into a single coherent picture of the world around the plane. For instance, if a radar detects an object ahead and the camera sees something at the same bearing, the system can confirm it's a single object and measure its distance and speed. The situational awareness is used by autopilots to make a safe maneuver. In effect, the sensors and perception systems serve as eyes and ears of the pilotless aircraft. It essentially is feeding an AI brain that we'll discuss next. Flying an aircraft isn't just about following a path, it's about making decisions. How to respond to changing weather. What if a system failure occurs? What if something unexpected is blocking the runway? In pilotless flight, artificial intelligence and advanced algorithms are responsible for such decisions, replicating a judgment of a human pilot. Current autonomous aircraft primarily rely on deterministic algorithms. Essentially, it's a very sophisticated rule-based system for normal operations. The flight management computer will execute the flight plan and respond to sensor inputs according to a pre-programmed logic. If wind shear detected, initiate go around. But increasingly, developers are integrating machine learning and AI to handle complexity of real-world flying. AI can be trained on vast amounts of flight data to recognize patterns and anomalies, and allowing it to make informed choices in nuanced situations. A notable area where AI is making inroads is in emergency and contingency management. Airbus's recent Dragonfly project demonstrated that an AI-driven system that in the event a pilot faints could take over, assess the situation, and even communicate with air traffic control. In their test, the autonomous system successfully managed an emergency descent and diversions. It analyzed factors like airspace restrictions, terrain, and weather, and then formulated a new route on the nearest safest airport and executed an autonomous landing. It also even radioed ATC and the airline's operations center to inform them of a new plan, effectively acting as a virtual pilot handling the entire incident. This showcases AI's potential to not only fly the plane, but to coordinate with broader aviation systems during critical moments. Research is also underway to imbue AI decision-making similar to experienced captains. Boeing, for example, has explored pilot AI concepts as early as 2017. Boeing's engineers were testing AI that makes pilot-like decisions in simulators and plan to trial it in real flights. The idea is developed algorithms that can handle complex problem solving, say deciding to perform an emergency water landing like a famous Miracle on the Hudson, a daunting challenge for any automation. While fully matching that incredible feat is a high bar, these AI systems are learning to handle engine failures, severe weather, and other rare events through simulation and real-world data. Another aspect of AI in pilotless aviation is continuous optimization. Autonomous systems can continuously adjust control surfaces and engine settings for optimal performance and fuel efficiency in ways humans couldn't easily do. For instance, an AI autopilot might make a minute throttle adjustment to account for air turbulence, or automatically re-optimize the climb profile to save fuel when it senses a lighter payload. Such micro-optimizes improve safety and efficiency over a long flight. It's important to note that in today's implementations, human oversight is usually still in the loop, often called human-on-the-loop model. The AI handles flying and immediate decisions, but a human can monitor and intervene at a high level if needed. As the technology advances, we expect AI to take on more of a decision-making burden, moving from handling routine tasks to tackling complex judgment calls under supervision, and eventually operating with fully autonomy in most scenarios. I hope you like this video, and if you have any questions, leave a comment below. And check out my buddy Hayden T-Tech. He made a video on actually how this affects pilots in the real world. And I'm sure he'll be able to answer a lot of questions too. Anyways, thank you for watching, and I hope you have a great day.